Hello students, the topic that we are going to discuss today is elimination reaction. So first of all, let us start with the definition of elimination reactions. Elimination reactions are those reactions which involve the removal of two atoms or two groups without being replaced by other atoms or other groups, resulting in the formation of a multiple bond or a ring compound. So for example, if we have an alkane which has two carbon atoms alpha and beta, and we have the leaving group Y and the hydrogen atom H, then after removal of the molecule HY, we get the alkene. Similarly, if we have an alkene and we remove HY from the molecule, we get an alkyne. These elimination reactions are from carbon atoms. We have other type of elimination reactions also, where the two groups are removed from other carbon atoms besides the carbon atom, from other atoms besides the carbon atom. For example, if you look at this, you have oximes which can release the oxygen bonded group to give cyano compounds, or it can be removed from cyanohydrines to give carbonyl compounds. Again, based on the position of the leaving groups as well as the type of elimination reactions, they can be grouped under as 1-1 elimination, where the two groups are removed from the same atom, whether it be a carbon atom or another type of atom. For example, if you look at this figure, the leaving groups hydrogen and chlorine, they are from the same carbon atom to form the alkene. Then we have 1-2 eliminations or beta eliminations, where the leaving groups are from adjacent carbon atoms. This 1-2 elimination reactions are the most common type of elimination reactions which are found. Then we also have 1-3 elimination reactions, where the leaving groups are from the first carbon and next to next carbon. So for example, we have a part of the Favorsky rearrangement of alpha haloketones, which will give the cyclic compound. Other eliminations such as 1-4, 1-5 and 1-6 elimination reactions are also found, and the end product are cyclized products, or we get ring compounds by these type of eliminations. So among all these type of eliminations which are based on the position of the leaving groups, as I said earlier, the 1-2 eliminations or the beta eliminations, they are by far the most common and most important organic reactions. So we will now discuss more importantly the 1-2 elimination reactions or the beta eliminations. So we first start by, again, the definition, that is, in 1-2 elimination reactions which involve carbon atoms, the atom from which the Y group is lost is usually designated as the alpha or the 1 carbon atom, and the other group, which is usually the second leaving group, and it is more or less the hydrogen atom, is called the 2 or the beta carbon atom, as we see in this figure. So in 1-2 elimination reactions, we usually omit the 1 or the alpha carbon atom, and we just simply refer them as beta eliminations. So based on the mechanism of the reaction of the beta eliminations, they can be further grouped into 3 main divisions. That is the E1 elimination reaction, which is known as elimination unimolecular. Then the second is E2 reaction, or the elimination bimolecular reaction, and the third one is E1CB, or elimination unimolecular of the conjugate base. So now let us discuss these reaction mechanisms one by one. We start with E1 mechanism. E1 mechanism is the beta elimination reaction in which the hydrogen carbon and the carbon Y bonds are broken separately in a 2-step process involving the formation of a carbocation intermediate, and this ultimately leads to the formation of the alkene by loss of the second group. The first step is the slow step, where the CY bond is being broken to give the carbocation intermediate, and the second step is the fast abstraction of the base from the beta carbon atom to form the alkene product. So the E1 reaction, it follows first order kinetics, and the overall rate of the reaction is determined by the slow first step and is independent of the concentration of the base that is being used in the reaction. So the overall rate of the reaction of an E1 reaction mechanism is rate is equal to K molar concentration of Rx, that is the substrate, here in this case an alkyl halide. So the two main factors which promote E1 reaction are, number one, the alkyl group in the substrate has to give rise to a stable carbocation, and number two, we have to use a good ionizing or solvating medium as the base. So now we will discuss the next E2 mechanism, that is the elimination bimolecular mechanism. In this type of reactions, these are the beta eliminations which involve a concerted single step process to form the corresponding alkene through the single state transition state. That means you have the substrate as you see here, then the base abstracts the proton from the beta carbon atom, and there is the simultaneous removal of the leaving group Y by the breaking of the CY bond, but this goes through the transition state where you have it here in the middle picture, and ultimately it leads to the formation of the product, that is the alkene, with the removal of the leaving group as an anion. So E2 reaction mechanism follows a single step process where the base pulls the proton away from the beta carbon atom, and simultaneously the leaving group leaves the alpha carbon atom with the electron pair through the transition state to form the alkene product. So E2 reaction mechanism shows a second order kinetics where the overall rate of the reaction is proportional to the concentration of both the reactants, that means the substrate as well as the base. So the rate of the reaction is given as rate is equal to K molar concentration of the substrate, here Ry, into molar concentration of the base that we use. So for example, if you look here, we have the bromopropane, whereby it goes through the transition state in the presence of the base where it abstracts the beta proton and then ultimately forms propene. So if we look at alkyl halides, then the rate of the reaction, or the faster the reaction of E2 follows, tertiary greater than secondary greater than primary. And also if we look at the base, since the base is also an important reagent here, so if we have the different types of base here, then the amide base has greater effect for E2 mechanism than OR minus, then OH minus. Now let us try to understand the third mechanism, that is the E1CB mechanism, that is the elimination unimolecular from conjugate base or of conjugate base. These type of beta eliminations, they occur when the carbon-hydrogen bond is broken first to form a carbanion intermediate, and then it is followed by a subsequent removal of the leaving group to form the product alkene. From this type of reaction, you can assume that it follows an E2 mechanism. Thus, we may assume that the reaction here follows an E1 type of mechanism. That is, it has a two-step process. The first step is the fast and reversible abstraction of the beta hydrogen by the base to form the carbanion intermediate, followed by the second step, which is slow and rate limiting, that is the loss of the leaving group to form the alkene. As you can see, step 1 is the abstraction of the proton by the base to give the carbanion intermediate. This is a fast and reversible reaction. Then step 2 is the removal of the, or the loss of the leaving group to form the alkene product, and the leaving group leaves with the pair of electrons. This is slow and rate determining. So the overall rate of the reaction of E1CB mechanism is found to follow second order kinetics. That is, the rate is equal to the rate constant K into the molar concentration of the substrate into molar concentration of the base. So this is a very particular example where you have a substituted alkyl halide to give the alkene product. The second step is slow, and this is the rate limiting step. Now we will come to the stereochemistry of E2 elimination reactions. We are dealing with E2 elimination reactions only because we are more concerned about the stereochemistry which are involved in this E2 elimination reactions. So when E2 elimination reaction occurs in acyclic molecules, they can occur via two of the following conformations. Number one, in the anti-periplanar conformation of the starting molecule, or number two, the syn-periplanar conformation of the starting molecule. As you can see, the anti-periplanar conformation is the first picture, and the second picture is for the syn-periplanar conformation. So you can see the position of the leaving group as well as the beta hydrogen to form the alkene product in both the cases. So you find that in the anti-periplanar conformation, the hydrogen and the leaving group Y, they are in opposite directions and in anti positions, while in the syn-periplanar conformation, the leaving group Y and the hydrogen is in the syn-periplanar conformation, and ultimately they undergo E2 reactions to give you the alkene product. So in most of simple acyclic cases, the anti-elimination is found to be much preferred. This is because for E2 eliminations that occur from the anti-periplanar conformation, number one, the elimination is taking place from the lower energy or the staggered conformation rather than from the higher energy eclipse conformation. Then number two, the attacking base, that is B here, and the leaving group Y, they are all far apart from each other. That is, they are in anti-position and therefore they are farther apart from one another. And number three, the electron pair which is developing to form the double bond in the final product, that is the CH bond is being attacked and the CY bond is being released. They are in opposite directions. So the hydrogen, the beta carbon atom, the alpha carbon atom and the leaving group Y, they are all lying in the same plane in the anti-periplanar position from that of the attacking base. There are some more examples where we have the E2 syn elimination. For example, it will depend on the ring size. So if we have cyclobutyl, then the syn elimination percentage of the product is 90%, then cyclopentyl gives 46%, cyclohexyl gives 4%, and cycloheptyl gives 37% of syn elimination product. Now, the third point, that is the cyclohexyl compounds which give only 4% of syn elimination, that is more or less syn elimination does not take place. It can be explained by the fact that these cyclic compounds can easily achieve the trans diaxial conformation. So the leaving groups, they are anti in position and they prefer to go by anti-elimination reaction. Another reaction which occurs via the syn elimination reaction, that is the pyrolytic syn elimination or thermal syn elimination. It is also referred to as EI elimination reaction, that is EI intramolecular. So in this type of reactions, they undergo pyrolytic elimination, that is at high temperatures. For example, if you look here, xanthates, they undergo syn elimination EI at around 200 degrees Celsius to give the final alkene product. Now let us come to the substitution reaction versus elimination reaction. What we have to understand is that for every organic reaction that is happening, there is the chance of different types of reactions that are taking place at the same time to give rise to a mixture of products. So when we are dealing with elimination reactions, there is always the chance of substitution reaction taking place at the same time. That is, elimination reactions are also accompanied by substitution reactions, and thus unwanted side products are always found while performing either elimination reactions or substitution reactions. So they compete. What we have to understand is that E1 elimination reactions, they are accompanied by SN1 substitution reaction, that is substitution nucleophilic unimolecular. This is due to the fact that both these reactions, they have a common carbocationic intermediate. So if it has to undergo E1 reaction, then there will be the elimination of the leaving group, and if it has to be substituted, then one group or the nucleophile will come and attack the carbocation intermediate. Thus, the carbocation intermediate will be converted into either of the elimination or substituted products. This is via different pathways involving different transition states. The next point is that E2 elimination will also be often accompanied by SN2 substitution reaction, that is substitution nucleophilic bimolecular. These reactions occur through parallel concerted processes involving entirely different and separate pathways. That means E2 eliminations will go in one direction and the SN2 reaction will go in another direction, and they have different mechanisms. So we have three main issues concerning substitution versus elimination reaction. So what are these? These are, number one, the factors that influence E1 over SN1 product ratio. That is, if you have factors that are more giving E1 products, then the factors which also give SN1 products have to be taken into consideration. Then number two, we have those factors influencing the E2 by SN2 product ratios. And third issue is the factors which influence the change of pathways from either E1 by SN1 to E2 by SN2 or vice versa, such that these kind of shifts often changes the proportion of the elimination or the substitution reaction products. Considering these three issues, if we take the first two issues, that is 1 and 2, the carbon structure of the substrate is of considerable importance as the proportion of elimination rises from going from the primary to the secondary to the tertiary. So if you have a tertiary substrate which can give rise to a tertiary carbocation or intermediate, then that will have a further chance of being eliminated. This is because of the fact that the transition state for elimination is stabilized by the relative increase in the number of alkyl groups on the carbon atom of the developing double bond. For example, in the dehydrohalogenation reactions of alkyl bromides using ethoxide ethanol mixture, the alkene products are formed as, that is 10% if you use the primary alkyl bromide, then 60% if you use the secondary alkyl bromide, and 90% if you use the tertiary alkyl bromide. This means that the rise in the alkene product is due to the increased rate of elimination and the decreasing rate of substitution. Now, why does this happen? That is because the carbocation that is being formed, or the transition state, is stabilized by the presence of the three alkyl groups in the tertiary alkyl halide used as substrate. Another factor which help elimination reaction is the substituents on the carbon structure of the reagent. That is, if we have a carbon structure such as C double bond C or C triple bond C or aryl or phenyl groups, then these groups can stabilize the intermediate or the transition state through conjugation. So these type of substituents will favor elimination reaction. For example, if you look at this, you have the primary alkyl bromide, that is ethyl bromide. In the first example, it gives rise to alkene, or the ethene here, and it gives only 1% of the eliminated product. But if you were to change it or bring the substituent phenyl group here, then we see that there is a 99% increase in the eliminated product. This is because the phenyl group stabilizes the developing double bond through conjugation of the aromatic ring. Another factor which favors elimination reactions over substitution reactions is increased branching in the Ry, that is the alpha carbon atom. This leads to an increase in the proportion of elimination in the E1 by SN1 reaction mechanisms. The explanation for this increase in the eliminated product is that there is an increasing stability of the transition state to form the carbocationic intermediate, thereby increasing the stability of the progressively more highly substituted alkene product. Another reason that can be explained is that the steric factor operating around this type of reactions is that it favors elimination over substitution. If you see here, the carbocationic intermediate has the carbon atom in an sp2 hybridized state. Therefore, if it has to go to elimination reactions via the E1 reaction mechanism to form the alkene product, here also the carbon atom is sp2 hybridized. But if it were to be undergoing the substitution reaction via the SN1 pathway, then the substituted product will have sp3 carbon atom. In the same manner, steric effects will also favor E2 by SN2 substitution reactions, that is E2 eliminations will be favored over SN2 reactions. Another factor which we have to take into account is the size and nature of the leaving group Y, because this is very important in E2 by SN2 reaction systems. These type of reactions, elimination reactions E2, involve the breaking of the CY bond. Thus, elimination reactions will be promoted if we have the following leaving groups in the order: tosylate, less than bromide, less than dimethyl sulfur groups, less than trimethyl ammonium groups. So if the size of the leaving group is much larger or bulkier, then eliminated products are favored. But if we have to take E1 by SN1 reaction ratios, it has been found that they are substantially independent of the leaving group Y. Another factor is the type of solvent that is used for elimination or substitution reactions. So E1 by SN1 processes, they are favored by polar ion solvating media, whereas E2 by SN2 processes, they are favored by less polar solvents. Then also, a change in the concentration of the base that is being employed for the reaction may give rise to different products. A base which was favoring E1 by SN1 reactions can shift to E2 by SN2 reaction just by a change in the concentration of the base. So if you look here, a higher concentration of the base that is favoring E1 by SN1 reaction can shift the mechanism to E2 by SN2 reaction. That is, if you use more concentration or more concentrated base, then E2 reaction products are obtained. Finally, elimination, whether it be E1 or E2 elimination reactions, it is favored over substitution reactions by rise in temperature. If you increase the temperature of the reaction, then the eliminated products are obtained. This is explained by the fact that elimination reaction leads to a more positive entropy term favoring a higher free energy of activation. Thus, an increase the temperature of the reaction give rise to elimination products.